The next subtopic, that is normal distribution. Okay, so consider this example. Okay, so from where to where we'll take a travel time example. Consider we'll take an example from Margao to here. So from Margao to Panjim. Margao. Okay, so we know that on an average, based on experience, this takes about 45 minutes if you go by bus. Okay, shuttle bus will take around 45 minutes. So now, most of the times when you travel between Margao to Panjim, say you take 45 minutes. Okay, so let us try to draw the histogram for this situation. Make it flat. So consider this situation. Most of the times we take 45 minutes. Okay. Sometimes during peak hours the traffic is little more. Okay, we end up in reaching in 46 minutes or something. I can say we'll go to 50 minutes. No, 46 will be. So sometimes it takes a little less, so 46 minutes. Sometimes there's some other traffic problem or something, it will take 47 minutes. Huh? Yeah, we'll go gradually there. So sometimes it takes a lot of time, like you're getting stuck at the signal and all, so it takes 50 minutes. Okay, so sometimes, like a very bad case, you can say it goes to 1 hour. Okay, you get stuck in a big traffic jam and all, it takes to 1 hour. Okay, and some very rare case will take more than 1 hour. Okay, a very thin case. Okay, so same way, sometimes the bus drives faster, you can reach in 44 minutes. Same way, little faster because you can reach in 43 minutes, like on Saturdays when the traffic is very less. Okay, so same way, there's a very less chance that somebody reaches in 30 minutes. Okay, this is in a very extreme case, like if you're traveling at 6 o'clock in the morning or something when there's no traffic at all. So 30 minutes it takes. Okay, so now if you try to convert this picture into a graph, a continuous graph, it will look somewhat like this. Okay, so the picture will look somewhat like this, where the peak is attained at this point over here is called a mode. Okay, this is a frequency distribution table. Mode is the most frequent value, means the number, it has the highest frequency. Okay. So if you look at this picture, it looks somewhat like this. Okay, so this is how it looks, and this is something what we call as a bell shaped curve. Okay, so now we'll define this a continuous random variable x having the bell shaped distribution is called as normal distribution. Okay, okay, so further definition, the probability density probability density function of a normal random variable x with mean mu and sorry, not mode, sorry, and variance sigma square is given by 2 pi sigma e raised to minus half x minus mu upon sigma the whole square. Okay, here okay, 14159. Okay, and E is 2.71. Okay, so this is an infinite expansion number, but we'll be considering only this first 5 digits. Okay. Note something here that this distribution depends on the value of the mean and the variance. Okay, it depends on the value of mean and the variance. Okay, because the mean and variance, they affect the kind of the bell shape you are going to get. Okay, let me give you all an example here down. So see, one clear thing is the variance, what it does is, note, mean is equal to mode distribution for the normal distribution, okay, thus the mean decides where the peak should be. Okay, in a simple example here, I'm fine. Where were you?
Attendance.
It's behind with them.
It's not this one.
Okay, so you can get this graph. Okay, so keep the mu1. So this is an example where mu1 will be less than mu2. Okay, so if your mean is less, the peak shifts to the left. Okay, in other words, if mean is higher, peak is okay. So basically the mean decides where the peak will come, whether it will come here at this point or at this point. Okay, the higher the value of the mean, the higher the value of the more to the right will be the peak. Okay, second, this thing about the variance, two, variance decides how wide The variance decides how wide the well will be. Okay. So for example, uh, sigma 1. Okay. So the higher the variance, the wider the well. Okay. And also it will become shorter. Okay, if you make it wide, it becomes short. That's what I'm saying. Why does it become so? The third thing is total area under the graph is equal to 1. Okay, total area under the graph is equal to 1. Uh, Total area under the graph is 1. So this is because the total probability is 1, the area under the graph should be equal to 1. Okay, so hence if you make the graph wide, this means high variance, this will make the graph short. Okay, so because if you make it wide, you're getting more area anyways, and if you make it narrow, Yeah, the graph will become tall. Okay, so the next thing is, and that's what you can see here on top, by the way. I should have mentioned this, sorry. Sigma 1 is greater than sigma 2. Okay, sigma 1 is greater than sigma 2. I'll write this over there. Okay, so that's what we said here. If the graph is higher variance, it will become wide. If it is low variance, it will become tall. Okay. Yeah. Next thing, fourth point. The graph is symmetric about the mean. Graph is symmetric about the mean. Okay, so what does this mean? Okay, so basically what I'm saying here is, okay, it means that these are mirror images of each other, and you can think of this as a mirror. This blue color thing here is a mirror. Okay, so basically if you keep a mirror in the center, what you can see on the left is what same as what you can see in the right. Okay, but the more technical thing over here is, the area to the left of the mean is same as okay. So in other words, what I'm saying is, paint this in two different colors. This green area is same as the yellow area. Okay. So the green area is equal to the yellow area over here. Okay, so what else is remaining? Another thing. 6. The graph tends closer to okay, it tends closer to 0, but it does not touch. Okay, so basically what is happening here is as it goes towards infinity, no. Okay, it will almost touch the axis, almost touch but not actually touch. Okay, this is because that exponential function never becomes 0. Okay, it is never equal to 0. Okay, so this is with the basic part of the normal curve. So now let's go to the thing that finding the what if I didn't finish. Because this, if you want to see the graph of e raised to minus x looks somewhat like this. It will never touch the x-axis. Okay, so let's go to the next thing, that is area under the normal curve. Okay, so okay, so we know that the area under this curve should give us the probability, right? Okay, so area under the curve of a probability distribution should give us the probability of something or the other. Okay, so if you want to find out probability of x1 less than x less than x2, okay, okay, uh, random variable with normal distribution. Okay, so this is nothing but it's the area under the curve. X comma mu. Okay, so this is going to be integral from x1 to x2. Okay, so now we have to integrate this 1 upon. Huh? Okay, so now we have to integrate this complicated looking function. Huh? What happened? What column? So do you all know how to integrate this function? Have you all done this integration before? So how you all will integrate this function now? Huh? Is there any formula to integrate this? Anything we shall learn? Any known trick works here? Okay, so actually you can't integrate it easily. Huh? Okay. So just write. I'll write it in right over here. Blue. I'll write it. The integrand is basically this function here. Huh? Because it is a continuous function. Okay. However, however, it cannot be however it cannot be integrated okay. Hence Okay. Now, what are these numerical integration techniques? No, they're not covered for you all, but they're covered for the BSc and MSc Math students. Okay, so we won't go to those techniques directly. We'll directly use the values which are available for us. Okay, so somebody has already done this and given us the values, so we'll use those values ready-made. Okay, but how those values are coming? That's coming from some method. Okay, which is not covered for you. Okay. Okay. So now, moving further, standard okay, so this is one very special important case over here. One special case of the normal distribution definition. Okay. The distribution of a normal random variable with variance 1 called as standard called as the standard okay. Okay, so that is mu is equal to sorry, mean is 0. Mean is 0 and sigma is 1. Okay. The standard normal variable is usually denoted by Z. Okay, so for this case, we'll be using the alphabet Z, not X. Okay. Okay, so basically, this case of N Z 0 1, this will be calling it as just a moment. Just check what this book uses. Okay, we'll use capital N for this case. Okay, now this notation varies from book to book, but anyways, we'll restrict ourselves to this case, this alphabet series. Okay. Okay. So now, okay, Z square, because all other terms over there got cancelled now. Z minus 0 upon 1 square it will be, that will be Z square. Okay. So now, area area under the standard normal curve. Okay, so now what we do is probability of Z1 less than Z less than Z2. Okay, so this is the integral to be calculated. So now we have predefined values here. So consider if you want to calculate this for any z belonging to one is z lying between minus infinity to plus infinity. The probability of capital Z less than z, okay, this is going to be given by minus infinity to z 1 upon root over 2 pi e raised to minus okay. Now this value is already calculated and it's available to us. This is called as phi of z. Okay, so basically what we are doing here is okay, sorry, in this case the mu is 0. Okay, mu is 0 here. Okay, so if you have any z here, Okay, the shaded region over here is phi of z. This will become minus infinity this side. Okay, so the graph from there up till the z value. Okay, so this is defined as phi of z values, and for z, wait, I'll say pre-calculated table. Okay, so there is a table available here with all the values. You see. Okay, so there is a table of this format which is there. This is available here, where values can be calculated from this. Okay. So all the values are given here. Now how to find the value, we'll do it in the problems. When you're solving problems, I'll show you how to exactly find the values for a given number. Okay, so now some properties of phi of z which will be used to calculate this. One, this is probability of z less than z, small z. This is directly defined as phi of z. Okay. So next, if I want to find out probability of z greater than z. Okay, so this is what now? This is what we have to see. So I'm choosing some z value here. Okay, I want to calculate the z greater than this. So basically what I'm looking for is Okay, so this is the area which we want to calculate now. So now what we'll do is we'll call this thing as we'll call it as A. Okay. Now this side, to the left of this is phi of z. Okay. The area to the left of z is always phi of z. So phi of z plus A is equal to 1 because the total area under the graph should be equal to 1. Okay. So what will be the value of A? A will be equal to 1 minus phi of z. Okay. So thus probability of capital Z this is going to be 1 minus phi of z. So in other words, what I have actually done here now is 1 minus probability of z less than 1. Okay, so in other words, if you can look at it, you can see this is 1 minus complement of probability of this is the complement of probability z minus okay. So the complement of z greater than z is actually z less than z. Okay. So this is done. Next, 3 probability of z1 put this in boxes. Okay, put all these formulas in boxes. When we're solving problems, we'll need them. Okay, so this is what actually probability of z1 less than z less than z2. This is integral from z1 Okay, so this is 1 upon 2 is to minus half AC square. Okay, so this what we do is we write this as two integral. Now this is properties of integrals, huh? Minus infinity till z2. I'll just write this as n. Huh? This thing I'll call it as nz. Okay, so these are properties of integrals, huh? So this can be written as phi 1, phi of z2 minus phi of okay, so the final thing over here will be probability of z1 the upper one minus phi of z2. Okay, this is property number 3. By the way, just keep a picture over here for this thing. For this case, huh? Okay, so here we'll take z1 Okay, so this is the area which we are trying to calculate. So next, 4. Probability of z less than minus z. Z is greater than 0, minus z is a negative number. Okay. Plus z. Okay, so notice this here. Okay. Since the graph is symmetric, okay. Now this we know is phi of minus z, and this we know is already calculated. This is from 2. Go fast. What are you? Couldn't sign. Allah the Vasantina. Okay, so next, so these are the four main properties. Next are consequences of these properties. Uh, Fifth one, probability of z greater than minus z. Okay. Wait. I should have written this. Golden sign. Okay, so probability of z greater than minus z. Uh, minus z. This should be 1 minus of phi of z. This is something what we already saw from 2, right? But what do we know from 4? Okay, these are shortcut properties. Okay, now the last one of this is 5, 6, 1. Probability of Z1 I'll just make a change here. Just write this as Z1. Not it for Z1. Okay. So what do we know from this? This is phi of Z minus phi of minus Z. This is going to be phi of Z minus okay, so probability of minus Z less than Z okay, so these are the 6 values. Okay, so just keep a note, for exams. Okay, so exams you will be given Z. Okay, so you'll have to calculate. Huh? 120 है. You will have to calculate the using above properties. Okay. So the last thing for today will be the transformation. You didn't write? Right. Okay, so the transformation. Wait. I'll just write this. So transformation to reduce random variable. Okay. With a mean variance sigma square, then Z will be equal to x minus mu upon sigma. Pause for the Okay, now how this transformation comes now, it might be a little difficult for you to understand because you'll have not done BS level this thing. This operation is called as change of and this denominator operation is called as scaling. So what is the numerator part doing is that if your graph is over here and this is 0, this x minus mu job, what it does is it shifts the graph to this point. Okay, and the denominator, what it does is you're dividing by some quantity, right? So that divider adjusts the height of the graph. The moment you adjust the height, the width automatically gets adjusted. Okay, so this is the transformation. So we'll stop with this. Okay, bye bye.